So let me just greet everyone, welcome you to the INA Wednesday webinar. My name is Debbie Carlson. I am president of the Institute of Nautical Archaeology, and it is terrific to see so many familiar faces and names. I just want to thank everyone for joining us today. The subject of today's webinar, as I'm sure you all know, is the Cape Gelidonya shipwreck. And this is, as I'm sure you understand, a particularly bittersweet subject because we said goodbye to INA founder George Bass less than 3 months ago. And Cape Gelidonya was the site that George excavated in 1960, together with Peter Throckmorton and Honor Frost and Ann Bass. They were actually on their honeymoon. Now, we feel George's absence every day in everything we do at INA, and he and his wife Ann are never far from our thoughts, but I have to say I know that he would have been very excited to be here today with us to learn from this top-notch team of scholars more about the site that meant so much to him, both professionally and personally. The Wednesday webinar is designed to last under an hour, and I know that some of you are literally on your lunch hour, so thank you for being here, and others of you are joining us from elsewhere around the globe. I know that some of you will have questions, and in order to accommodate everyone in the time that we I'd like to ask that you type out your question using the chat function in Zoom, and then we will relay the questions to Dr. Hirschfeld or the members of her research team. And if you want your question to be directed to a specific scholar, then please feel free to indicate that in the chat. But we will be fielding questions using the chat function in Zoom. Now, speaking of 1960, do you like my Zoom background? That's the Bodrum Castle, circa 1960. You can download this wallpaper and other INA backgrounds at the INA website if you'd like to. That's nauticalarc.org, www.nauticalarc.org. Okay, so without further delay, I would like to introduce my very good friend, Dr. Nicolle Hirschfeld, Professor of Classics at Trinity University and INA affiliated scholar. Dr. Hirschfeld is responsible for assembling this excellent team of scholars spearheading new research on an old ship, the Cape Gelidonya shipwreck. Dr. Hirschfeld, all yours.
Hi all, can you hear me? Am I unmuted? Deb, can you hear me? Yeah, okay, great. So thanks, Deb, for this opportunity, for letting us present our research. And let me first convey our team's appreciation to the INA Institute and to all the people at INA who make things happen in the field, in the office, and in the boardroom. Thank you. The person most vital to the project that we will be discussing today is, of course, George Bass. I miss him sincerely and immensely. And in fact, sorry, I chose this particular image because for me, it conveys the enormity of what this individual accomplished. And there is the old Vierazon anchored very close to the wreck site of Cape Gelidonya and these huge cliffs as symbols of what George had to overcome in order to make this project happen. Deb has already introduced me, but my purpose today is to provide a brief summary of the Cape Gelidonya shipwreck project, intended for those less familiar with this shipwreck, and thus provide context for the more specific topics presented by my collaborators. George entered into a long history of explorations underwater. And I point here to the stone plaque found in Ostia, which is the port city of Rome. It dates to about the 1st century BC, and you see fishermen pulling a net that includes fish, but also a statue out of the sea. And below are 2 images of excavations at Lake Nemi, undertaken in the early Renaissance. And there's a wonderful book published by John McNamara about the Renaissance origins of underwater archaeology. For underwater archaeology, there were 2 significant technical advances. In the 1830s, Augustus Seabed invented a helmet fitted with a release valve and to a full-length watertight canvas diving suit, and that allowed prolonged stays underwater, albeit tethered to a hose that delivered air to the diver. And the first modern excavation of a shipwreck in 1900 at Antikythera took place using that hard hat helmet diving. It was a nationalistic venture, sponge divers salvaging statues for the National Museum collections. The most famous find from the shipwreck, the calendrical computer, was discovered afterwards in the debris coincidentally brought up with the statues. In World War II, Émile Gagnon and Jacques Cousteau invented the aqualung, the predecessor of scuba gear today, and divers could enter the sea unfettered. And that led in the 1950s to the excavation of a shipwreck at Grand Congloué. And using this new technology, the archaeologists was still on board this ship, and the people diving were professionals, the archaeologists directing the divers below. And this separation of archaeologists from divers contributed to serious confusions in understanding the stratigraphy of what was later understood to be 2 separate shipwrecks, one sunk directly on top of the other. So the third pivotal moment, and the one we'll be concentrating on today in underwater archaeology, was at Cape Gelidonya in 1960. And there, George Bass, Peter Throckmorton, Honor Frost, Joan Duplatt Taylor conceived of excavating a shipwreck according to the standards and methods of terrestrial archaeology. And this meant attention to documentation and recording in situ, recovery and conservation of all finds to allow the full reconstruction of the ship's hull and its cargo. Crucial was the archaeologist was working on the seabed, directly involved in the documentation and recovery. And here I've depicted on the left, you see the copper ingots. These funny looking things are ingots. We'll talk a lot about that today. This was the primary cargo of the ship. They were found in a concreted mass on the seabed. That mass was raised to the surface, it was cleaned, and then the original lading, as recorded on the seabed, could be reconstructed on land. Copper and tin were the vital materials of the Bronze Age, like oil in the 20th century, or now lithium for batteries and the rare earth metals for making computer chips today. And what all archaeologists do is we reassess old theories in light of new discoveries. George looked closely at the relatively contemporary documentation for the exchange of copper ingots, primarily images in Egyptian tombs. And this is the tomb of Hui, and here you see a man carrying a copper ingot of the same shape as those found at Cape Gelidonya. He noticed that the dress of these people carrying and exchanging these ingots was Syrian in nature. And by looking further at the personal possessions, lamps used on board the shipboard, a cylinder seal, and these are pan balance weights for a scale to measure weights. Looking at the personal possessions or objects in use on board the ship, all pointed to those who were on the shipboard working and traveling within the orbit of Cyprus here, and the Levantine coast. Archaeological method, everything is important to the story. Everything is collected, not just the statues. There were none on the ship, but this ship had broken tools, scraps from metal object production, tools for working metal. These two are clearly not ancient, but they show these are bits from the metal production, this sprue. It's these little bits that you get if you pour a mold. And this is called a swage block, and it is for fashioning copper tubing. So all these finds led George to interpret the ship as that of a traveling tinker, a man, presumably a man, collecting broken artifacts for eventual recycling, dated by carbon-14 dating to about 1200 BC. 2 decades later, in 1987, during a break in excavations at another late Bronze Age shipwreck, well, it's the late Bronze Age shipwreck, located a day's sail to the west at Uluburun, George and his best friend Claude Dutuy, a member of the original 19 expedition, went for a one-day nostalgia visit to Cape Gelidonya. George and Claude dove first and poked around the wreck site, hand fanning in the sand. Those on deck did not expect anything but happy grins when the divers surfaced, but instead each came up holding a pan balance weight. Other divers brought up more finds, and the quick visit proved that the site had not been as thoroughly excavated as had been thought when a storm ended the 1960 campaign. Also, decades of experience working underwater had made George and his colleagues more adept in seeing objects engulfed by seabed concretion. So 4 more return visits to the site, lasting from 5 days to 2 weeks, yielded more significant finds, including a sword, which is the only weapon on board, 2 large courseware stirrup jars, and an anchor that was found about 100 meters away. So the site of the ancient shipwreck is here, and around the corner right here is this projecting just below well, it's not projecting, it's just below the surface of the water, bit of rock, and it seems that the ship ripped her hull open against this projection and then limped sort of around the corner until she sank. So all those discoveries convinced us that the site merited a full-scale re-exploration, which we undertook in 2010. A half century after the initial excavation, co-directed by George Bass, Harun Özdaş, and me. And I just, again, need to mention Jamal Pulak, without whom that project could not have taken place. The emotional highlight was when the 3 surviving, at that time, members of the 1960 team dove on the wreck once more. But the purpose of that 2010 expedition was to scour the seabed, every single nook and cranny, to recover what else remained of the shipwreck. And that's a unique aspect of shipwreck archaeology. Shipwrecks are a deliberate assemblage, and it's possible to recover them almost in their entirety. On land, only tombs are comparable. We found out that the scatter of finds was much wider than originally understood. This is the area of the 1967 excavations, and you see that the finds scattered down along and all the way to that point of rock. Now, the finds are in the Bodrum Museum. And being conserved and studied. And I just have to mention Tuba Ekmekçi, the director of the Bodrum Research Center, which is INA's Institute for Research, and the finds are stored in the Bodrum Museum. Tuba Ekmekçi, we couldn't manage without her. And Tuba, I hope you're not embarrassed by the picture, but you really are a superstar, so I couldn't resist putting that in there. And Esra Altanat and Asu Selan, who are part of our conservation team. It takes a while to conserve objects that have been soaking the seawater for 3 millennia, and that was the first bit after 2010 to about the first 6 years were taken up with the conservation. And now we are working on the analysis. And the specialists today are the 3 amigos to the right and a couple others who will be talking about what we are learning from the scientific analysis. There are other members of the team, Bartek Lis and Yuval Gorin, who are working with the ceramics. So this is just intended to be kind of a hors d'oeuvre of the sort of things the meal will be serving when we finish working on this project. And I'd like to turn this over to Nick Blackwell.
Thanks a lot.
Yeah.
Oh, go ahead.
No, I just want to make sure you're unmuted, but clearly you are. Good.
Okay. All right, so that means everyone can hear me. My name is Nick Blackwell. As you can see on the slide here, I'm an assistant professor at Indiana University Bloomington. And I joined the project a couple years ago to investigate the non-ingot metal assemblage. And you can switch to the next slide. And in particular, I was interested in part because my dissertation at Bryn Mawr College focused on second millennium BC metal tools from the Aegean, Eastern Mediterranean, and Anatolia. And so certainly the Gelidonya assemblage was very critical to that. And one of the things that I was particularly are the metal hoards in Greece and Cyprus, the Eastern Mediterranean, because there are a lot of similarities between the assemblage in these hoards and what we find in the Gelidonya assemblage. And this is something that Bass recognized early on. One of the things that I'd like to emphasize at this point is how much larger the Gelidonya assemblage is. When George Bass published the Shipwreck in 1967, he had a catalog of copper alloy objects of 257. That number is now up to 480 after these later surveys and returns to the site. And it remains a mix of tools and weapons and tripod fragments, things that you can see here. But again, perhaps the biggest takeaway is that it resembles a hoard, like a metal assemblage on land, but it's substantially larger, 12 to maybe 10 to 12 times larger. You can go to the next slide. And of the non-ingot assemblage, tools make up the largest proportion. So of that 480 number, you can see that 71% or 343 objects are tools. And of that category, you can see that the largest proportion of that are agricultural tools. These are picks, these are hoes, plowshares, pruning hooks. You see some of these examples, in addition to some other ones like an axe, which I classify as a construction tool here. And the presence of so many agricultural tools is really intriguing because they have a pretty strong distribution, at least in the Eastern Mediterranean, as coming from Cyprus. And this is certainly part of Bass's original interpretation because much of this assemblage was broken and very much scrap metal. At the same time, there are more or less complete objects. So that's something that we have to wrestle with. Next slide. Emphasizing sort of the Cypriot connection that you can see with the tools are a nice little example of, or a nice, I should say, data set of inscribed tools. And Cassie Donnelly, who's a PhD candidate at the University of Texas in classics, Nicolle and I recently wrote a paper that's under review that looked at the inscribed tools. And you see a few examples here, and more or less all these inscribed marks are Cyprominoan or Cyprominoan-like. There seems to only be one inscription. You can see that on the pruning hook on the bottom right of the screen. And this is interesting in as it relates to sort of our understanding of what's going on with these metals when it gets on the shipwreck. Are these marks produced once they're acquired on the ship, or are they produced while they are still in use? And we think that latter interpretation makes the most sense because of the other sort of, the rest of the examples that you don't see on the screen. They're mostly fragmentary objects with these inscribed marks, but it does further sort of emphasize this Cypriot connection. Next slide. And then perhaps most intriguing, at least from my perspective, and I think it ties in nicely to the overall interpretation of the shipwreck, as well as what we will see with the ingot materials, is the fact that we have evidence in some of these tools of what I think is deliberate breakage or fragmentation. It's unclear if this is occurring sort of on Cyprus or at another port of call before getting on the ship. But what you can see at least if you look at the images on the left, I think are pretty clear examples of cuts into tools. You see the top left, you can see that sort of cut, I think probably from a chisel, beginning to sort of sever the socketed area from the blade. The example in the bottom left looks like perhaps you can see that hole in the center, perhaps made by an awl or a punch. And then the examples on the right are evidence of repetition of sort of types of fragments. In the top right, you see a number of examples of the tips of plowshares or hoes. Now, perhaps these were naturally broken during use. That's a possibility. We also are exploring whether or not they're intentionally broken at this spot. Likewise, the example on the two examples on the bottom right of the screen show socketed sections of a tool, and this is a sort of an area that's often broken just between, at the transition from a socket, a part of the tool, to the blade. And we don't necessarily know the full implications of this at this point. That is this our tinker merchant who is manipulating these objects on the ship for metallurgical reasons or market reasons? We hope to do some statistical analyses of both the measurements and the weights moving forward whenever we have an opportunity to return to Bodrum. And so with that, I will pass it along to the next speaker, Emre.
Thank you, Nick, and thank you, Nicolle. Can everybody hear me okay?
Yes.
Okay, okay, great. So in this part, I will focus on the copper ingots, which, as Nicolle mentioned, constitute the primary cargo of the ship. And we'll talk about our new database and the new chemical and microstructural studies of these ingots. Next slide, please. The copper cargo of the ship consists of around 1,200 ingots with a total weight of about 1,200 kilograms. They belong to the two common ingot types of the period, namely oxide and bun ingots. As these two charts demonstrate, in terms of both quantity and weight, these ingots are predominantly found as fragments rather than complete examples. So the majority of the ship's ingots were cut or broken into smaller pieces by their traders. There are also a large number of fragments that we cannot attribute to either the oxide or bun ingot types due to the lack of diagnostic features. In terms of weight, however, these unidentified fragments contribute relatively little to the total cargo, as they are usually the smallest pieces in the assemblage. Next slide, please. We cataloged the ingot assemblage in a new database, and this is how one of the about 1,200 entries in the database looks like. On the left-hand side, we have the general description of the ingot and physical measurements, including those specific to the ingot type in question. On the right-hand side, we have the information on surface features, including coverage, distribution, and size of blisters and gas pores, which are leftovers of the casting process. Further observations, such as whether the piece was hammered or cut or display surface inclusions, such as dunnage, are also included. Hence, the database is organized in such a way that it provides as much information as possible on the production process and post-production treatment of the ingots. Finally, our general comments and notes from previous studies, if available, of course, are provided. Next slide, please. These are the instruments used in the chemical and microstructural investigations of the ingots. About 800 of the ingots were analyzed by means of portable X-ray fluorescence instrument at the Bodrum Research Center of INA, that is shown on the upper left. Around 10% of these were selected for higher precision analysis by means of inductively coupled plasma mass spectrometer at Koç University that you see on the upper right. For this analysis, samples of a few milligrams were taken from the ingots and dissolved in acid, as shown on the lower right. The microstructure of the ingots were examined by optical microscope and scanning electron microscope at Koç and Boğaziçi universities. On the lower left, you see me and the operator of the scanning electron microscope at Boğaziçi University during the examination of one of our ingot samples. Next slide, please. The results of the chemical analysis showed that the samples are composed of nearly 100% copper, as one would naturally expect from a raw copper ingot assemblage. The only and interesting exception was a single bond ingot that turned out to be bronze rather than copper. But for now, let me focus on the so-called trace elements, chemical elements present in lower concentrations than 1% in the ingots. The comparison of the Cape Gelidonya ingots and their previously studied counterparts from the Uluburun ship reveals significant differences. On these charts, the Gelidonya ingots shift more towards the top, displaying their generally higher arsenic, cobalt, and iron concentrations. Likewise, they shift more towards the right due to their higher antimony and sulfur concentrations. These obvious chemical differences indicate that the ingots from the two ships were either produced of copper from different sources or by different smelting and melting processes. Next slide, please. The differences between the Cape Gelidonya and Uluburun ingots are augmented when their microstructural properties are compared. On the left, the microstructure of an ingot cross-section from the Uluburun assemblage is shown, as published previously by a German research team. The common characteristic of the Uluburun ingots is the frequent occurrence of slag inclusions, iron silicate minerals left over by the smelting process. Interestingly, slag inclusions are not attested in our investigation of the Cape Gelidonya ingots, indicating that they were either produced by different smelting or melting processes, or may have undergone post-production refinement. On the other hand, copper sulfide inclusions that were frequently detected on Cape Gelidonya ingots were absent in the Uluburun assemblage, once again raising the possibility that the ingots of the two ships were made of copper from different sources. These issues and questions will now be elaborated on by my colleague, Dr. Joseph Lehner. Thank you.
Oh, thank you very much, Emre, and thank you to everybody else and everyone here at the at this really a great presentation and everyone involved. I'm particularly happy to be able to present some of our new data on the provenance question, as Emre has just mentioned. My name is Sepp Lehner. I'm coming to you from all the way from Sydney, Australia. And I'm an archaeometallurgist by training and a field archaeologist working on a number of different projects, as you can see in the map here. And I've been working with the Cape Gelidonya project since about 2015 or so, I think, is where that places everything. Next slide, please, Nicolle. When George Bass excavated the Cape Gelidonya wreck and its diversity of metal finds, of course, one of his principal questions was the provenance of copper metal ingots. Knowing at the time that there were a plethora of copper sources around the Mediterranean, there was only a couple that were really likely candidates at the time. And George had already early on came to an informed conclusion that Cyprus was probably the foremost location of the raw materials necessary to produce a lot of the copper aboard the wreck. But in 1967, there was only emerging onto the scene in archaeological science a way to actually test this. Next slide, please. Now, one of the early innovative collaborations that George built, and there were many, was with Bob Brill, a foundational figure in isotope archaeology, who knew that one could fingerprint copper metal and its original ores using the geological age of the trace amounts of lead in copper. And it wasn't until the Isotrace laboratory at Oxford University, a massive effort led by Noel Gale and Sophia Stoss, that the question of copper provenance was taken on in the scale that was truly needed. The Isotrace laboratory confirmed in a number of papers and a lot of conversations in the scholarly literature that nearly all oxide ingots are consistent with Cypriot copper. Next slide, please. Now, our efforts as part of the Cape Gelidonya project here draw inspiration from these first initial efforts. And we bring in some of the latest instrumentation with high precision to examine copper provenance in detail. And this is being done in part as a collaboration with Dr. Moritz Janssen of the German Mining Museum. As you can see from this chart here, the Cape Gelidonya ingots, whether oxide, bun-shaped, or indeed the fragments that Emre had just talked about, are by and large consistent with a singular region of Cyprus, the Solea axis of Western Cyprus in particular. Next slide, please. Yet new discoveries are being made as we conduct our work. These unpublished results demonstrate that there's a new source of copper aboard the Cape Gelidonya wreck. The geological age of the lead and the copper of these samples are old, around 600 million years old, making the copper inconsistent with all of the presently known sources around the Mediterranean world. This has already been observed from the earliest known oxide ingots from Crete, thanks to the work at Oxford. So this presently unknown source of copper could possibly be linked to Precambrian copper ores of Arabia. But we must stress that this kind of technique isn't good for verifying precisely where materials are coming from, but it helps us isolate and discriminate other sources that are potentially candidates. So the technique has really shown that a lot of these other source regions are incompatible with these current measurements. Next slide, please. Yet one of the fascinating aspects, again, of the Cape Gelidonya wreck is the fact that when you look at the ingots and compare them against the scrap metal, what you find couldn't be more dramatic. The ingot metal is, by and large, composed of Cypriot copper, yet the non-ingot metals run the gamut from sources across the Mediterranean region. Next slide, please. Now, focusing in on comparing the Cape Gelidonya ingots against the Ullebrun ingots, what we see is an important difference. Both of these ingot assemblages are by and large consistent with Cypriot ores, yet there's a shift. So like the elemental chemistry that Emre was talking about, and the isotopic chemistry is showing this important shift as well. So what is the story here? What is going on? Next slide, please. So if we focus in on, and we know that the Solea axis is an important contributor to the copper of both the Cape Gelidonya and Ullebrun wrecks, we can examine this further. Next slide, please. In particular, the Apliki mines in the Solea region, we can see from this modern mine the great variety of ores, from oxidized ores all the way down to the original primary sulfide ore body that's associated with this particular source. Next slide, please. And knowing how, as we go from the primary sulfides and as they become oxidized over time, what we can actually do is use different isotopic methods to track that particular change over time. Next slide, please. And thanks to the work of Moritz Janssen in particular, who is really leading a lot of this particular research, we can use the isotopic ratios of copper to demonstrate how we can shift from oxidized ores that were used at the surface down into the deeper sulfide ores. And what we see is that by and large, the Cape Gelidonya ingots, the ingot metal, the primary metal, is associated with sulfidic ores at that time. Next slide, please. And when we compare that against the Ullebrun wreck, what we can see is that the same sort of big shift. The Ullebrun materials are really most consistent with oxidized ores, these kinds of ores that would have been present on the surface, whereas the Gelidonya ores that are represented in the copper metal of the ingots must be the deeper sulfide mineral. So we think that we can trace the transition from superficial oxidic ores down into the deeper sulfides by comparing the Ullebrun and Cape Gelidonya ingot cargoes. Next slide, please. Another focus of the work that we're on is dealing with the tin. So the image on the right shows the very famous and well-known Ullebrun tin ingots, from the oxide shapes to the bun ingots as well. There's other shapes aboard the Ullebrun wreck. At Cape Gelidonya, we have, by and large, a large fragmentary data set as a function of not only the corrosion and denuding of those materials, but probably the original cargo was quite fragmentary itself. So where is the tin coming from? Next question, or next slide, please. Of course, tin is well known across the whole region, from Western Europe and Cornwall all the way to Central Asia and Afghanistan and the Badakhshan region. Several smaller occurrences are throughout the region as well. This remains a big question of where the tin is coming from, but new isotopic methods are available to help essentially test this question even further, and we've managed to test one of the tin ingots so far aboard the wreck. Next question, or next slide, please. And using lead isotope ratios again and combining it with more computational geochemistry to understand what's happening, is that we can confirm that at least one of the samples aboard the Cape Gelidonya wreck, in terms of its geological age, is consistent with the Variscan orogeny, in terms of geological age again, so that 380 to, well, I had about 380 million years ago or so. And that rules out a lot of the Central Asian sources. And so we think that we have to begin to surmise that potentially other sources are possible. Sources that are consistent must be the same as those that we know from the Southern Levant, thanks due to the work of Daniel Berger and the rest in Mannheim as well. So with that, I will pass it on to Sam Martin, who has been working on a lot of the 3D data.
Hello, everybody. Good to be here. Thanks for having me. My name is Samuel Martin, and I am here at the University of Arkansas in lovely Fayetteville, so it is daytime for me, unlike some members of our team. And I am just one member of the Cape Gelidonya 3D project, formally or informally known as CG3D, lovingly known as CG3D. And I have spent the past 4 years on this project since the summer of 2017, primarily digitally documenting and archiving the ingot cargo from the Shipwreck via the production of 3D models. Next slide, please. We've been approaching this process through two different but complementary methodologies for the larger materials, such as the oxide ingots. We have been using photogrammetry, also known as structure from motion. This part of the project has been primarily spearheaded by Dominique Langis-Barsetti, who will be speaking at the end of today's presentation about some of her work. On the other hand, we have been able to capture smaller objects, items, and fragments using an Artex Spider structured light scanner, seen in profile in the left image. And yes, that is me with much shorter pre-pandemic hair. Next slide, please. This high-resolution 3D dataset has been a great way to archive and document the Gelidonya's archaeological materials. Not only are these scans able to capture superficial details, they are also able to emulate texture and color, sometimes in resolutions up to 8K, which is twice as high as your typical 4K television. It has provided a new avenue for researchers from abroad to examine the cargo without the need to lug several tons of ingots to and from a lab. Thankfully, us scanners have done a lot of the heavy lifting for worldwide research. And so far, we have scanned hundreds of these objects, which has amounted to several terabytes of high-resolution data for the shipwreck. Next slide, please. As you can see from these images, we are able to accurately capture sub-millimeter topography while reducing the visual effect of surface anomalies that might make analyses of diagnostic features more difficult. Seen on the right is one of the wreck's metalworking tools, likely a swage, scanned using structured light. Structured light uses an array of laser emitters to capture shape, distance, and texture triangulated in real time. This allows us to have these models made at scale as we're producing them. The system, structured light scanning, offers us a good combination of speed and precision, allowing for the quick acquisition of multiple scans at high resolution without much concern for ambient light conditions and the need for any kind of drawn out calibration. Next slide, please. Transferring the ingots from the material to the digital world has allowed us to see them literally and figuratively in a brand new light. We're able to perform spatial analyses on their surfaces that highlight important features such as impressions, incisions, and landmarks. And these 3D models are able to be exposed to different types of point source lighting and can be explored using new graphical tools such as global illumination and ambient occlusion to highlight features through the artificial exaggeration of shadows. Next slide, please. So again, for both structured light scanning and photogrammetry, these models are created to scale. This means that we can produce digital elevation models, but that we can also measure volume and surface area, and it can be fairly quickly computed without the need for any kind of specialized equipment. And this data volume, things like volume, surface area, shape, and topography are essential variables that we can use to compare and contrast typologically similar ingots. Next slide, please. Now, this slide, Structure from Motion, is going to talk a little bit about the photogrammetric work that Dominique has been doing. And this will be really important for some of the really cool things that we're doing and we'll be talking about towards the end of the presentation. Photogrammetry, or structure from motion, uses 2D images taken from a variety of angles to reconstruct a 3D object or scene by tracking the position of thousands of features from one image to the next. The motion parallax created by that movement of the camera between different angles around the target object then allows the processing software to accurately calculate the distance of each point on the object from the observer. Once all of these are plotted out in three-dimensional space, a model of the object emerges. And in order to get this level of detail and get the complexity of the topography we're looking for, between 150 and 400 photos were taken of each ingot, depending on how topographically complex it was. And with all of that material gathered, it was processed in a program called Agisoft Metashape, which is a commonly used tool for photogrammetry to actually run the algorithms to put these models together. Next slide, please. So seen here, we're able to produce some very cool spatial data. These digital elevation models provide us with a unique view of ingot production and surface topography. Shown here, we are clearly able to delineate impressions and its depth relative to the complex surface of IN25. Additionally, we can analyze the distinctive curvature of the ingot as well. Next slide, please. While impressed and incised marks have received a lot of attention in this project since the ingots were first brought up from the seafloor, digital tools and display methods are showing them more clearly than ever, allowing us to refine the initial assessments and tease out more subtle features, such as possible tool marks located on the surface of the ingots. And so now I'm going to turn it over to Lucina Bowland, who's going to get more into the nitty-gritty of some of the analyses we are doing with this 3D data set. Thank you.
All right. Hi, everybody. My name is Lucy. I am a PhD candidate at the University of Arkansas studying biological anthropology. So I'm not an archaeologist, but I was brought onto this project because I'm really interested in shape analyses, particularly using a method called geometric morphometrics, or GM. So GM is really popular for data sets with biological specimens, but it hasn't been used outside of biology that much. So I was really excited to work on the Cape Gelidonya project because this assemblage offered a really interesting way to use GM kind of outside of the norm. So next slide, please. All right, so what is GM? So GM is a powerful statistical tool used to study shape using coordinate data. So when you start a GM analysis, the first thing you want to do is called landmarking, which is placing points at areas of interest along your specimen. And these points become coordinate data. So since we're working with three-dimensional data, our landmarks become XYZ coordinates. You can think of it like mapping out the area of interest for your study. So wherever you place your landmarks, that is where you, that's what's being analyzed in the study. So after you've landmarked, you're left with what are called raw landmark configurations, which is what you see in A here. So the next step is to separate shape from size, position, and orientation using what is called a general Procrustes analysis. And this is one of the things that's so great about GM is that you can mostly isolate shape from these other potentially confounding variables. So when you run a general Procrustes analysis, it takes place in three main steps, which are what you see in B, C, and D here. So the first step is to translate your raw landmarks so they all have the same centroid size. Or sorry, so they all have the same centroid. So you're trying to orient them around a central point. So you're taking out that variable of orientation. The next step is C, it's scaling your landmark configuration. So they all have the same centroid size. So centroid size has a really kind of verbose definition, but just know that it's the main size metric used in GM. And so again, you're just trying to remove size as much as possible by scaling them all to a common size. And then finally, the last thing you want to do is rotate your configurations so they all have the same average position. So after you've done this, you are left with mostly just shape. And so you can run your analyses on the shape. Next slide. Okay, so coming to the Cape Gelidonya project. So we know the distribution of known oxide ingots extends across the Mediterranean with networks inland into Central Europe and the Balkans. And we know from isotope analyses that most of the copper sources for these ingots come from Cyprus. So we know the material seems to be coming from one common source location, but these ingots also vary pretty substantially in shape, as you can see here. And we don't really have a good explanation for why most of the copper seems to come from a common source, but the shape of the ingot seems to vary so much. And so this really raised the question for us of, does shape change substantially over time from a single producer region, or are there multiple workshops operating simultaneously? Next slide. So to address this broader research focus, our study had two main questions. So the first one was, how can we describe ingot morphology empirically and reproducibly to systematically compare across assemblages? So how can we compare all these different known assemblages with all of these different shapes? And the second question that we had was, can the qualitative topologies developed by George Bass be corroborated using geometric morphometrics? So George Bass qualitatively developed three main shape categories for these ingots. He called them 2A, 2B, and 2C. But we wanted to do a quantitative analysis to see if these shape categories held up, and so make the analysis more reproducible. All right, next slide. So this figure is an example of how we landmarked our ingots. So we analyzed our ingots as completes, halves, and wholes. So the complete ingot is what you see with all of the landmarks all the way around it. The halves are what you see in blue on the left side of the screen. So we call it 2 ears plus the neck of the ingot, which is denoted by that arrow there. And then the quarters are the red portions of the ingots, so kind of 4 corners. And we oriented all of our ingots whenever possible using this mark that's shown here. So the quadrant to the upper left, we called quarter 1 or quadrant 1. Okay, next slide. Okay, so just really broadly, what do the results tell us from this? So it tells us that half and complete ingots can be classified into Bass typologies using these methods, but for whatever reason, quarters cannot. So that's something that we hope to explore further, but yeah, okay, next slide. So these last few slides are just really quick results. So this is a principal components analysis graph showing PCs 1 and 2 for the complete ingots. So you can see that on PC1, these cluster really, really nicely in shape space, right? So you have 2C on one end of the PC axis, 2B on the other end, and then 2A, which George Bass kind of thought was intermediate between them anyways, kind of falling where you would expect it to, right? And then next slide. And then the same is true for the ingot halves, right? So once again, on PC1, these cluster really, really nicely in shape space. So we know that these categories that George Bass originally developed hold up using these quantitative analyses. And so we hope to use these for further projects to kind of help explore the shape variation across these Mediterranean ingots. And with that, I'll pass it to Dominique.
Hi, my name is Dominique Langis-Barsetti. I am a PhD candidate at the University of Toronto. I joined the project as one of the 3D modelers about 4 years ago. And although I have been mainly focused on the ingot so far, this last portion of the presentation relates more to a bit of a treat that we built for ourselves based on some archival image from the 2010 resurvey of the Gelidonya shipwreck. Next slide, please. So what we ended up doing is, after Nicolle kindly took a deep dive into the 2010 archives, we pulled out all the large shots of the seafloor, and using this collection of about 350 photos, we were able to build a 3D model of the Cape Gelidonya site itself. Next slide, please. What we've been able to accomplish is essentially create both an orthophoto and a 3D model of this very important site. Now, previously it had been exclusively documented using 2D photographs, but with collecting all these photos and using photogrammetry, which we talked a bit more earlier, we stitched everything together and created this much more immersive version of the site. Next slide, please. So this little endeavor came with some challenges. For one, the photos were taken over 2 days by the project photographers back then, so Sheila Matthews and Susanna Snowden. Now, they did an excellent job of taking all the overlapping photos that we needed to create a photogrammetric model. So combining these data sets, which at the end of July, everything was stitched together and created the model that we ended up with. Next slide, please. So what we were able to do is essentially benefit from some of the quirks of archaeology and the particular 2010 resurvey of the Cape Gelidonya site. As archaeologists, we have this useful tendency of very systematically taking tons of photos, either to document objects or the site itself. In 2010, what played in our favor as well is because digital cameras were becoming more prevalent, but yet were not everywhere as they are today, which meant that at the time of the resurvey, there were 2 digital cameras in the water. What is very important for that is that the software we're using, which is Agisoft Metashape, doesn't really like building models from different cameras and will not deal with cameras that don't have embedded metadata concerning the quality of the lens and its different distortion parameters and all of that. Lucky for us, all that information is encoded already in digital photographs. So the software was able to handle the different types of lenses and stitch the model together essentially by itself, because they were taken over 2 days with 2 different cameras. We generated 2 different models, which were then stitched together to create this complete landscape of the seafloor. Another useful quirks of archaeologists is that we tend to have very interesting scattered all over sites, whether they are recognizable objects or, in this particular case, scaled objects. So what I believe were planning frames of 1 meter side. So using those, we were able to assign a scale to the model that we generated from these archival images. One of the very useful things about photogrammetry is that, unlike 3D scanning, it is to a specific size of objects. Photogrammetry will generate models at any range of scale you want, assuming you have appropriate images. So you can generate objects that are millimeters or sub-millimeters in size if you have photos that are small enough, or you can cover kilometer-wide landscapes as long, again, as you're able to scale them, which we were able to do thanks to, well, archaeologists leaving scales everywhere on the sites they excavate. Next slide, please. So very quickly, because we're reaching the end of our allotted hour, our 3D model is preliminary and is not perfect, but is still very interesting to us because it was generated from archival photos that were never meant to be used to generate 3D models using photogrammetry. So we cobbled everything together and ended up with a model that we are very satisfied with. There are some issues with it. For instance, the 2 days worth of models don't perfectly match together. There's a seam on the mesh, but it is still precise enough that objects that were left on the seafloor, like those scales, as you can see, show up in the topography of the model. Now, this particular forum of online presentations across several continents is not the best to show 3D models in all their glory. But for those of you interested, we posted the 3D model itself on Sketchfab, which you can access following the link on the screen at the moment. So I will let you explore this slightly lower resolution version of the Cape Gelidonya seafloor at your own leisure. And I believe I will pass it on to Nicolle, back to Nicolle for concluding remarks, as we are very close to the end of our allotted hour. So thank you. Nicolle, you're still muted.
Sorry about that. Thank you. Sorry, we've really filled our time here. Debbie, I don't know if there are any questions that anyone has to ask in a couple minutes.
We are looking for questions in the chat. I don't see any at the moment, but we have maybe 2 minutes. So if anyone has a question they would like to pose to the scholars we've just heard from, there's so much fascinating material here. And I have to say that George himself would have so enjoyed this and was such a proponent of the kind of interdisciplinary research that we are seeing here. He often said that we should surround ourselves with people who know more about what we're doing than we do. And I think that's a great example of what's happening with the Cape Gelidonya shipwreck. So one question is simply about future plans for the site itself.
We have no future plans for the site itself. We know we didn't get everything. That trail goes very, very deep. At this point, we are just going to concentrate on, I mean, it's a great question, Shelley. There's stuff down there and it trailed off and it would be wonderful to go back. It's under deep layers of sand and the depths are quite great. So there are no immediate plans to return, but hopefully we can, this old ship still has new questions and new material. And so hopefully we can provoke people to have an interest in returning there. We're going to concentrate right now on finishing up with the wealth of material we have in our hands. And I would invite anyone who has more specific questions for any one of us. You can send them. Deb can give you our addresses, or you can contact me. I forgot to put my email, but we're easily found on the internet. Or through the INA Archaeological Society.
So I just shared the 3D link that came to me. I put that in the chat, but I will just echo what Nicolle said about being easy to reach. And let me just also solicit suggestions for future INA webinars. If you have ideas or suggestions, feel free to send those to me. My email address is president@nauticalarc.org. So I think with that, Nicolle, do you have anything else you want to add?
Now, here's to George.
Amen.
Team and teamwork. We can't, it's just, you got to have a great team. And he encouraged that above all. He really encouraged students. So thank you. Thank you all. Bye.
Thank you for joining us, everyone. Have a great day. Stay healthy. Stay safe.